Hello, this is Jack Jackson. We're back again, continuing our look in inferential statistics to look at hypothesis testing. In the previous video, we looked at the classical test statistic approach for hypothesis testing, specifically with a two-tailed one-sample z-test. And this one, we're also going to look at a two-tailed one-sample z-test, but we're going to do it the alternative way, which is a p-value method. So if you remember, in the classical test statistics method that we covered in the previous video, we computed x-bar values, or actually finally we did it with z-scores of these values, and we computed boundary A and B values, which are either sample mean values or actually the z-scores of those sample mean values, corresponding to critical points which corresponded to critical regions of the graph. And in those critical regions, the probability that x-bar or z-score lands in those critical regions was the probability alpha. And so we ended up comparing either x bar value to x bar value, or what we actually usually do is z-score to z-score. Now in this video, we're going to talk about the p-value method. And this time, instead of comparing z-score to z-score, we're going to compare probability to probability. We're going to compare a p-value, which is a probability value, to alpha, which is also a probability. Okay? And so let's look at the example here. So let's continue with the last example. And the last example from the last video, I should have reused this slide there, but let me back up and I'll show you the slide with the setup. All right, here's the setup. The setup for the problem is right here. We're making pistons with known historical data. The pistons individually are distributed normally with mean of 4.25 and standard deviation 0.12. At least that's been historically what's happening. We take a sample from what we think is this population, or it might be this population, of sample of size 16. We find a mean of 4.31. We notice it's larger. The question is it large enough that it triggers us to think that there's some special cause of variation present, and something has basically happened to the process to make these pistons bigger than they've been in the past. Okay, and if it's so, we want to know it so we can make an adjustment. But we don't want to make an adjustment if this is just because of some normal causes of variation that would normally happen. Okay, so in the p-value, what we do is we just simply compute the probability of getting that value or something more extreme. Okay, now since this is what's called a two-tailed test, the probability that the p-value is going to be twice what we get right here. So what we're going to do, we're just going to do a normal CDF from 4.31 technically to infinity. I just used 1,000 here. Okay, or we could use 10 times the hypothesized standard deviation plus the mean. Hypothesized mean there, I just went extra and went 1,000. And then 4.25 is the hypothesized mean, and this 0.03 is the standard deviation, not of the individuals, but of the x bars. So that's the given sigma divided by the square root of n. And that turns out to be 0.02275, and then we double that to get the p-value. So the p-value is here. It's less than alpha, so that's enough to reject the null hypothesis. Here's the picture. Here's our x-bar here, and the probability that we just computed was 0.0228. That's the probability to the right of that. Then there's a corresponding probability on the left, but those two together add up to be the p-value, so that's why we had to double it. Now notice that what we're doing is we're comparing the p-value, which is this blue area, to the alpha value, which is the red area up here. So in the classical test statistic approach, we found the boundaries of the red region. The red region has area alpha, or probability alpha, and then we found that gave us the red regions, and then we looked at our x bar and see if it's in there, or we did the same thing for corresponding p-values, z-values. Down here, what we do is we calculate these areas here, these probabilities, and that gives us our p-value, and so we can just compare p-value to alpha. So the decision criteria is basically this. If you have a small p-value, you want to reject the null hypothesis. How small? Well, less than whatever you choose for alpha. So in this case, if p is small, less than alpha, like we had here, then we reject the null hypothesis in favor of the alternative hypothesis. We conclude that there is sufficiently strong evidence to accept the alternative hypothesis and reject the null. The probability that this sample came from the hypothesized distribution is below our threshold. It's low. So the probability of making type error is small. P is less than alpha. So we reject the null hypothesis. On the other hand, if we have a large p-value, how large? If it's greater than or equal to alpha, then we fail to reject the null hypothesis. There's not enough evidence to support the alternative hypothesis. The probability that the sample came from the hypothesized distribution is above our threshold, and so the probability of making a type error is too big. P is greater than alpha. So if P is less than alpha, reject the null hypothesis. P greater than or equal to alpha, we fail to reject the null hypothesis. And the smaller p-value is, the more evidence, or the stronger the evidence is, to support the conclusion that the alternative hypothesis is true. Now, there are a couple of advantages that are distinctly there for the p-value approach. The value chosen for alpha is somewhat subjective. If the p-value approach is used, and the p-value is reported in the study or the publishing your results, then the reader of the results can easily compare this to a different chosen alpha value without having to redo the entire test. So if you did the test and you said, well, we used a p-value of 0.05, and other researcher says, no, 0.05 does not meet my standards, I want to use an alpha value of 0.01, the reader does not have to redo anything. They can just use the p-value you came up with, compare to their choice of alpha, and see if they would reach the same conclusion. And so for this reason, I prefer the p-value approach, and when we get later to calculator shortcuts, it prefers it as well. Now, there are different variations on a theme. There are two-tailed tests. That's when the alternative hypothesis is that mu is not whatever mu naught is. A left-tailed test is the alternative hypothesis is that mu is less than mu naught, and a right-tailed test is mu greater than mu naught. With the left-tailed or right-tailed test, the entire, if you think back to that blue picture, the entire p-value, that blue area, is over on, if it's a left-tailed test, it's always on the left of our test statistic. And if it's a right-tailed test, the entire p-value probability is that blue area that will all be on the right tail to the right of our test statistic. In the example we just did, that p-value was split half and half. Half to the right of our test statistic and half to the left of a corresponding value on the other side. Now, that's the first variation we can make. The other variation we can make is if we have different assumptions, or if we're measuring different statistics. Rather than doing the mean, we might be doing, say, the variance, or we might be testing proportions, for example. And so there are different distributions for those depending on what's going on. But the basic ideas of this example carry over to new situations. The p-value is always relates to at least the probability of a type 1 error. Okay? And we want to compare it to our threshold of the acceptable limit for probability of type 1 error, which is alpha. Okay? A p-value is always the probability of getting a sample, getting a result, that value of what we actually got, or something more extreme. Now, there are some basic assumptions for a z-test or z-interval. Remember, a z-test, we're testing a sample mean against a known population mean. A z-interval, we're forming a confidence interval for a mean of a population. So they're both dealing with means. The distribution of sample means is approximately normal. This is a good assumption if the distribution of individuals is nearly normal or the sample size is large, greater than 30. And the population standard deviation unknown. Same assumptions for both a z-test and a z-interval, basically. But this last assumption is usually not a good assumption And a little bit later on down the line, we'll get to what's called the t-test or t-interval, which will show us what we can do in that particular situation. Before we do that, however, we're going to work through a few more examples in the next few videos.